So continuing on, we're going to dive into interrogating association claims. And to start, I'm going to make a comment on construct validity as it relates to statistical validity. And the important thing to note here is the importance of the operationalization of variables. And so let's say that I wanted to measure whether someone has COVID or not. And so a valid operationalization of this would be to simply give them a test and have the test determine whether or not they have antibodies, which is a determinant of whether they have COVID or not. And so that would be a valid way of operationalizing that variable. However, a less valid way would be to simply ask, hey, do you have COVID? Right? And the reason that this is less valid is because we know that people can be asymptomatic, not presenting symptoms, and still have COVID. And we know that an individual can be infected, but yet have symptoms displayed. And so we would likely get a lot of no's, even though the people who said no are infected, right? And so that would be less valid. And so the reason why this is important for statistical validity or in relation to statistical validity is that the statistics that are calculated from the measures or the measure that you had taken from the operationalization of your variables the statistics are reliant on a valid operationalization of your variable. And a good phrase to keep in mind, this is something that has always stuck with me, is the phrase garbage in, garbage out. So the garbage in, if the data is bad or the collection of it, the operationalization of a variable is not valid, it is not proper, and not very accurate, that is the garbage in, and the statistics that you get from that is going to be the garbage out. And so moving on from there, we're going to jump into statistical validity. And first up is relationship strength. And so this is essentially how strong a relationship between two different variables is. And it's measured by effect size, which can also be an R value or Pearson's correlation coefficient. And so an effect size can be a value that ranges from -1 to +1. And so going back up here, we've got this little graph here that indicates a positive association. As we discussed earlier, positive association, this one a negative association. And so for a positive association, this can be a number from 0 to +1. And not including 0. And then for a negative association, it'll be between 0 and -1, not including 0. And so that is the effect size, the strength of a relationship, which is going to be -1 to +1. And the closer that number is to either +1 or -1, the stronger the effect is, or the stronger the relationship is between two variables. And now a p-value, what that tells us about our effect size is basically whether or not this effect size that we have calculated or read within a study is truly significant, whether it matters. And so we're going to scroll back up here to number of hours studied versus test score. And let's say hypothetically that this effect size or R value is equal to 0.8. So this is a very high effect size. And something that I need to mention as well is that when you are comparing effect sizes, it's relevant to understand what field of study your effect size is out of. So for psychology, A weak association is going to be an effect size of like 0.1. A moderate is going to be 0.2, and then a high effect size within psychology is like a 0.4. And now back to p-values. So we've got our R value of point A, the strength of relationship between number of hours studied and test scores. And let's say that our p-value equals 0.01. What this tells us essentially is the whether this value of point A is significant or not. And so ultimately, the traditional cutoff for p-values is 0.05, so 5%. And so since our p-value here is 0.01, this 0.0 or 0.8 is significant, is statistically significant, given our threshold of 0.05. And in addition to that, if you would like to know how to interpret the p-value, what the p-value is ultimately saying is that assuming that there is no relationship between number of hours studied and test scores, so an R value of 0, assuming that that is the true relationship, this p-value is the probability that we obtained this 0.8. So the probability of obtaining this value of 0.8 is very low if we're assuming there is no relationship between the two variables. And so that is p-value as it relates to effect size. And so p-value is where we go to see whether an effect size is significant or not. And now we're going to ask, how precise is this estimate? How precise is this effect size? And one way we can quantify that is with a confidence interval. And so what a confidence interval is essentially a range of values around our effect size that the true population parameter is likely to lie. And so when thinking about how we calculated effect size, we calculated this effect size from a sample from the population, a sample from our desired population, in which we are truly trying to find a statistic that is true to the population. And so the confidence interval tells us whether or not we have got an interval or an interval around our effect size is going to, where the true population parameter is going to lie. And so back up to this number of hours studied versus test scores, let's hypothetically say we've got this R value of 0.8, and our confidence interval ranges from 0.75 to 0.85. And you can see that 0.8 would be right in the middle of these two values. It's centered in this confidence interval. And so a standard procedure for confidence intervals is the 95% confidence interval. And so this is going to be the range at which this is calculated. And so what the 95% confidence interval tells us, and what this number ultimately tells us, is that if we were to repeat the survey, we would expect 95% of those calculated statistics to fall within this range here from 0.75 to 0.85 hypothetically for this study. And so now moving on, replication. And so we're going to go over this a little bit in a little bit more detail at the end, but ultimately replication is going to either increase or decrease statistical validity. And so if we were to replicate this study here, if we were to do it again, and we found an R value of 0.7 and a p-value of 0.01 again, meaning that this are 0.01, meaning that this statistic of 0.7 or effect size of 0.7 is statistically significant. This ultimately increases our statistical validity for the original study. Contrary to this, though, let's say we replicated the study again and we found an R value of 0.05, which is a very low effect size. And the p-value was 0.1, so 10%. So that is above our threshold of 0.05, meaning that this is non-significant. This would decrease the statistical validity of our original study. So that's how replication can affect statistical validity. And another thing that I forgot to mention about confidence intervals is that sample size affects confidence intervals. And so if we were to look at this confidence interval up here again, from 0.75 to 0.85, which is around 0.8, if we were to increase the sample size, this interval would decrease. So let's say we increase the sample size and our new confidence interval is 0.78 to 0.82. So 0.8 is still in the middle, but our confidence interval is a lot smaller. And since our confidence interval is a lot smaller, this is increasing the precision of our estimate. We've got a more narrow range of value where the true population parameter can lie. And so that is going to ultimately, it's going to decrease that range and increase our precision. We're more precise. So continuing on to outliers. Ultimately, outliers are going to negatively impact the strength of our relationship. And so to illustrate how outliers can affect the effect size or correlation coefficient, I'm going to hop over to the study which you'll be reading for the practice form 7. And so on this plot here, you can see on the x-axis, we've got the Gini index, which you will learn is the index for income inequality. And then on the y-axis, you can see number of cases, number of COVID cases. And so you can see that the general trend line here is already drawn. It's this red line through here, which indicates the relationship between these two variables. And so if you look at this line, you can see that all of these different dots are oriented around it, and that the general trend is up and to the right. So as Gini index increases, the number of cases increases as well. And as a reminder, it's just an association. So the Gini index is associated to number of cases. And so to illustrate how outliers can potentially affect this association, I'm going to draw just a random dot all the way up here to the top left of this graph. And so since this dot is not in congruence with the general trend of dots in the line, this is going to have a impact on the effect size. It's ultimately going to decrease it. And a way that you can visualize it is that this dot is ultimately going to pull the line on the left-hand side up, and then on the right-hand side of the graph, it's going to push it down a little bit. And so let's say that the new trend line might look something like this. And so as you can see, this dot pulled this line up on the left-hand side and slightly down on the right-hand side, and is thus decreasing the strength of the relationship as it is an outlier. It is not in congruence with the other points on the plot. And now jumping into restriction of range. I'm going to use the same graph to illustrate how a restriction of range can change the relationship, the effect size, and as it relates to statistical validity. And so as we look at this graph, once again, we've got the general trend line here that goes like this. And then we've got our x-axis, which goes from 42 to 52. But now let's say that we want to restrict the range, the variability of values on the x-axis. So instead of 42 to 52, let's say we want to go from 47 to 52. So now we're going to draw a line up through here, which cuts off all of the values on the left-hand side. And so we're interested from 47 to 52. And now we can see that all of these dots here on the right-hand side have a new general trend, which is still positive up and to the right. However, you can see that the association is a lot more steep. So you can see that the general trend line is still up and to the right, but it is nowhere near the same trend line as we had originally going through here. And so that's how restricting the range of a variable can affect the relationship between the two. And so it could either strengthen or it could weaken the relationship. It just ultimately depends on the variable spread throughout the scatter plot. And so that is the restriction of range. And now another thing that you can see are nonlinear associations. And so everything that we've been looking at up until this point, the number of hours studied versus test scores, this is a linear association because it's a line. And if you remember a bit of algebra class, you can think of this line as the equation y equals mx plus b. And these are also linear associations or hypothetical ones, just kind of depicting this one as a positive linear association, this one a negative linear association. And so these are linear line associations. Now we can jump into nonlinear associations or curvilinear associations. So these are going to be associations between variables that are not in a straight line. And so I'll draw an example to illustrate this. Let's say on our x-axis here, we have age. And on our y-axis here, we have athletic ability. So we know that athletic ability typically peaks around your mid to late 20s-ish. And so when you're about your mid 20s, let's say 25, let's say your athletic ability is about right here. So you're about peak athletic ability. And so the number between the numbers between 0 and 25 are going to increase. Obviously, when you're 0 years old, you have 0 athletic ability. But as you age up to 25, this is going to increase. And so you're going to have dots that are going up towards this peak over here. And then as age increases past middle age, or not middle age, but your mid-20s, athletic ability is going to slowly decline, right? And so as you can see, you cannot just draw a straight line through this. You can see, though, that the overall trend is going up and around here. So in the beginning, from 0 to 25, it's going up and to the right, but after 25, it slowly decreases. So athletic ability slowly decreases as age increases past 25. And so this is an example of a nonlinear or a curvilinear association.